Welcome back. In the last video, we discussed the process of creating a transformer encoder. And according to the paper, and according to the figure, the transformer encoder is a combination of alternating blocks of MSA, so equation 2, and MLP, equation 3, which we have as PyTorch code. And then we created it as pseudocode. And I finished with the challenge, or leaving you with the challenge, of trying to implement this block using PyTorch code. So I trust you gave it a shot. And if you already did, if you think yours is working, feel free to jump to the next video. Otherwise, let's now do it together. We're going to initialize our class Transformer Encoder block, and we need an input here for embedding dimension so that we know what embedding dimension we're using. So this is going to be hidden size D from table 1, and we're using 768 for VIT base, which is going to be the theme for all of our other hyperparameters. Then we need number of heads. Why is that? Well, because the Transformer Encoder block contains an MSA block. So we need to tell it how many multi-attention heads we have. And then we go MLP size. This is for the MLP block. So by default, this is going to be 3072, which is from table 1 as well. Table 1, this is also from table 1, where it lists the hyperparameters. Table 1. And then we have MLP dropout. Dropout is an integer as well, 0.1. This is going to be from table 3 in the paper. And then finally, we have the attention dropout, which by default is actually 0, but we're going to leave that in there just in case we wanted to add some dropout later. And then we can run super.init, and now we can start to create our MSA block from equation 2. And this is so exciting because we can now start to put together all the pieces of the puzzle. We've got equation 1, 2, and 3, and now this is the reason why we turn equation 2 and 3 into PyTorch blocks. Watch how quickly we can create the MSA block. Create MSA block, and this is going to be equation 2. So self.MSA block is going to be equal to, now this is the class that we wrote before, multi-head self-attention block. Then pass in here, embedding dim equals embedding dim, which is just the input up here. Number of heads is going to be num heads equals num heads. And do we need anything else? Oh yeah, attention dropout equals attention dropout. And that is our multi-head self-attention block. And what did we get wrong here? Oh, is this a capital H? Beautiful. So that's equation 2. We just replicated this block here. Of course, we haven't got the residual connection yet. We're going to get to that in a minute. We'll define that in the forward method. So now let's create the MLP block, which is going to be equation 3, of course. So self.mlp block equals MLP block. And then what do we need to pass in here? Well, we've got our embedding dimension, of course, because the transformer keeps a constant embedding dimension throughout the entire architecture. MLP size equals MLP size, and then dropout equals MLP dropout. Wonderful. And there's equation 3 created. So now we have to stitch everything together by creating a forward method. So forward, taking self and x, some sort of input. Now we'll go x equals self dot, what comes first? The MSA block takes x, and then also plus x. Now where does that come from? Well, that's the residual connection. Residual connection, also referred to as skip connection. And if you've heard of the architecture ResNet, this is what introduced residual connections, and it's where the term ResNet comes from residual connection. That's another popular computer vision architecture. So there we go. If we jump back into here, that's that connection there, just adding the input to the output. And then we can do the exact same for self.msa or MLP block plus x. Residual slash skip connection for equation 3. Look at us go for equation 2. So all of that build up allows us to create the transformer encoder in 23 lines of code. And this could probably even be reduced a little bit more if we really wanted to. that residual connection could be implemented within the block here. So let's run that and let's make sure it works. One of the ways we can do so is by getting an input and output summary. And luckily we have a great method for that. So create an instance of Transformer Encoder block, because this combines a fair bit of code behind the scenes. So we will go Transformer Encoder block equals Transformer Encoder block. And we're just going to leave it with all the default hyperparameters. That's going to just set it there. And then we can get a summary using torchinfo.summary. So this is why way back at the start, we imported, or get set up, we installed torchinfo. So we can see an input and output summary of our different layers. So let's go summary of our model equals Transformer Encoder block. And then I'm going to pass in an input size. What can be our input size? Well, this is going to be 1197768, not the size of our image, because what's going to go into our Transformer Encoder block here? Well, it's going to be the output of the embedded patches. So that's why we're creating an input size of 1197768. So this is going to be batch size, and then number of patches in the sequence, that is, and then the embedding dimension on the end there. And so we can get some column names here. We'll type in, the first thing we want to know is the input size of different layers. We also want to know the output size of different layers. And while we're here, let's get num params. And is the layer trainable or not? It should be, because all of our layers should have requires grad equals true. And then we'll just set some aesthetically pleasing parameters here, such as column width and row settings. We'll get an output of each of the variable names, so we know what layers are in our Transformer Encoder block. So you ready? Our first Transformer Encoder block. This is so exciting. In 3, 2, 1, let's go. Do we get a summary? Oh, look at that. Isn't that beautiful? So it starts off with an input shape of 1197768 and finishes with that output shape. But notice how it gets manipulated as it goes through the MLP block. That's probably the biggest change in shape, because as it goes through the linear layer, we have an MLP size of 3072. So our image representation, our patch or sequence of patch representation, gets expanded here, and then it gets compressed as the output. So look how many parameters our model has. That's just with one Transformer Encoder block. And we've created it quite swiftly with this section of code because we leveraged the power of PyTorch's modularity to create equation 2 and equation 3 as reusable blocks. So do you see how far we've come? We've replicated the first 3 equations so far. You might already have a hint of how to do the last one with PyTorch code. So we've done exactly what we wanted to do. We have turned images, text, and math into reusable PyTorch code. Now, of course, in the overall Vision Transformer architecture, there is multiple Transformer encoders stacked on top of each other. So I'll let you think about how we could possibly do that, stack a bunch of the Transformer encoders on top of each other. But for now, let's in the next video I want to show you a way we can make what we've done even shorter. But no secrets. I'll save that for the next video. I'll see you there.